All right. Thanks very much. It's interesting to be here, even though remotely. And it's a first school actually where I'm sort of preaching to the audience that is mostly involved in direct detection. And I will be doing something of a less focused lecture than IKEAMS, and I will discuss more today the dark sector physics, and this would be including not only the direct detection, but also but mostly today search of the particles that may accompany direct detection, such as particles mediators and so on, dark matter mediators. And here is the plan for two lectures. So today we are going to be talking mostly about the setup, and tomorrow there will be a lecture on more of the connection to dark matter of dark sectors, and will be sort of heavy on Cosmo compared to that. And so I will use PowerPoint for lectures and iPad for exercise. So, all right. So let's just say a few words about the evidence for new physics. New physics is elusive so far. We have a standard model that is based on the product of the three gauge groups, and it's a well-established paradigm. Well, the actual evidence for new physics, interactions of particles and fields that sort of step outside of the standard model field content, comes from the neutrino physics and cosmology. Oh, sorry. And this is, of course, an enormous subject to cover in two lectures, but a lot of reference literature exists. So if I scroll back to the start of my talk, I would advertise recent review, a rather large review on this topic of dark sector physics. Very well. So since 2012, and continuing on, we have a very, very solid evidence of the last missing block in particle physics of the Stern model, and that's a Higgs boson. Over here, you see, for example, the signature from the CMS collaboration of the 4 lepton events where the invariant mass can be reconstructed well, and you can see the Z peak, the broad peaks from basically double production of Z bosons, and that particular peak is from the Higgs. This is a huge momentous discovery in particle physics, as basically the last missing piece of the Stern model, when the last unknown parameter it has been determined. And you can say that so far Higgs shows no internal structure whatsoever consistent with the Stern model. So it is then also a new type of fundamental force, Yukawa force, mediated by the Higgs. Then at the same time, no new physics at the LHC has been seen. So here is an already dated example of a search done at the very start of the LHC at 7 TeV. You can see that's the basically a dimuon or dielectron dimuon channel, where you see a beautiful rise and the shoulder. This peak is, of course, the Z peak. And then you are trying to find new resonances that you know, if you go to the left, it will be like J psi and upsilon resonances and so on. And then 1 decade later, at 91 GeV, you have a beautiful peak, Z peak, and now the number of the Zs produced at LHC is staggering. It's in the billions, and now you're looking for something like a new physics. If new physics is again a spin 1 resonance, you would see another rise of that nature at high energy, but this curve continues below, and currently the limits stand above 3 TeV or even 5 TeV in some cases. So no new physics, in particular in this channel, no new physics for SUSY, which stands for supersymmetry, yet we are convinced that new physics does exist, and the clues for new physics come from, as I already mentioned, precision cosmology, where a 6-parameter model was sometimes called lambda CDM, correctly describes a huge number of cosmological data. However, many of these parameters do not belong to the stellar model, right? And that's an important part of it. Now, neutrino masses and mixings is another good example of that there are new physics beyond stellar model, and well, one can sort of argue with me and say, oh, well, neutrino masses are predicted in the stellar model if we allow the right-handed neutrinos to be part of the stellar model. This is somewhat a semantical sort of take on it. I define stellar model without right-handed neutrinos, so we don't know if the right-handed neutrinos exist actually, but we do know that the neutrino masses and mixings exist for sure, and therefore that I would declare an evidence for physics that steps outside of the content of the sort of traditional content of the stellar model. Now, there are theoretical puzzles, strong CP problem, of which you will hear more during this school. Then there are various unsolved problems, such as vacuum stability inside the stellar model, maybe very strong hints on unification of forces that tells you that maybe there is much more to our theoretical construct. Maybe there is a more unified, more complex in terms of the number of particles, but maybe more economical in terms of structure of the theory, things standing at extremely high scale, 10 to the 16 GeV and so on. And then, of course, there's a lot of discussion on the smallness of the Higgs mass relative to high scales, which sometimes referred to as a gauge hierarchy problem, and that motivates a lot of theoretical thinking. And then, of course, there are also sort of checkered history of anomalous results that there are discrepancies with what you would predict in cases where you can calculate, for example, stellar model contributions very carefully, and chiefly among them stands the muon G-2 problem, where this year we have seen a confirmation of the basically old Brookhaven result, where the data and the predictions are disagreeing, with data being about 3 to 4 sigma larger than the predictions. But this is none of that of these anomalous results amount to evidence of new physics to the same degree as precision cosmology and neutrino physics. All right, so here's somewhat also dated data from first Planck satellite release. This is a very well, it's a part of the precision cosmology, very precise measurement of the 6 parameters of the lambda CDM model. The relative height of the third peak in temperature correlation spectrum actually translates into the measurement of the cold dark matter, and you can see how many digits there are. They are beyond the main parameter, which tells you basically that the existence of cold clustering matter in the universe is well established. You can vary it. Well, here the baryons are varied, but even with existing data degeneracy, it's the knowledge, the error in the knowledge does not exceed a couple of percent. So great. So we put an exclamation sign here. Oops. Very, very important. However, linking dark matter to particle physics is not easy. Why is that? So we have 23% of dark matter in the universe, and that with some computer simulations, possibly we can somewhat, with order one kind of precision, not better, translate to the structure of the observed galaxies, even though there are some problems with simulating small galaxies and so on, and substructure of beyond smaller than the main galactic scale. Well, we have to extrapolate here, and then the search for the dark matter done at various underground labs, very specific dark matter, like a few GeV mass dark matter, is done really at scales that are much smaller than this. By somehow got cut here my scale, but we have to make an extrapolation of 19 orders of magnitude. It's clear that such an extrapolation can be only done using a theoretical framework. You cannot just say, all right, here is this, and we just do this, right? So you need a theory as a first input to do that extrapolation. So what I'm going to be doing regarding theory is to bunching the dark matter into three different categories. Well, there are more categories, but among the particle dark matter, these are the leading categories. So I will bunching that with respect to the sort of the history of the abundance and how it's got generated. Are the new particles that you want your dark matter to be? Were they in the were there abundances in the early universe where you go to temperatures much above the masses of these particles? Were that normal? Normal meaning that this species was most likely thermalized. The number density of this dark matter relative to the number density of gammas, for example, the most abundant species in the universe, would be sort of order one, and then subsequent annihilation of dark matter leads to the freeze out and the residual abundance of dark matter. This is called WIMPs, as you must have heard from the Akim's talk. And then the interesting part is that sigma v times for annihilation on the order of 1 picobarn times the speed of light. That this type of cross section gives you up to like a factor that is not very different from one. This type of cross section gives you a very much a correct abundance of dark matter. Now, the interactions can be, the initial abundances can be very small. Imagine something like 10 orders of magnitude smaller abundance than or couplings than for WIMPs. In this case, the particles may never actually reach thermal equilibrium, not enough time for these small couplings to make its way and thermalize these particles. And in that case, there can still be this particle as a legitimate dark matter candidate due to the sort of thermal leakage of the Stern model fields with a sub-Hubble rate, sometimes called freezing, to the basically to the thermal bath of dark matter, which created subdominantly, and then it sort of gains over with time on the Stern model because it is quickly becoming non-relativistic. So this is what I call super weakly interacting massive particles, or sometimes called freezing dark matter. And then there can be a possibility that the number of, for example, very light particles, such as axions, can be much, much larger than n gamma. And that is possible only for bosons, because you need a condensate for that. And this is possible only if couplings are very, very small. These guys are not thermalized. But then subsequent expansion of the universe makes this sort of you can think of axions as the classical field initially displaced from its minimum, and the Hubble rate is the viscosity. So once the Hubble rate starts dropping below the mass of the dark matter particles, the field starts oscillating, and the oscillatory behavior of the scalar field at rest corresponds to a bunch of temperature zero particles, which later on acquire some velocity due to the gravitational collapses and so on or whatnot. But the important part that provided very small coupling and very large abundances and small masses, you can also achieve dark matter, and that's called the or you can call it super cool dark matter, right? Because it's developing from the super cool state. Okay. So very well. There is, of course, this is a very, very broad view on it, and for each of these categories, lots and lots of work has been done. For example, the WIMP category has been analyzed to a great detail, and here is various examples. So when you say WIMP, if you think particle physics, you have to ask yourself, all right, do I know something about how this WIMP got generated? So here is an example of WIMP interaction with the Stern model specified up to a particle that does this interaction. Remember, for WIMPs, we need two dark matter particles to go to two Stern model. Well, it doesn't have to be two, but this is something to keep in mind. So these are various examples. You can have Z boson mediation, Higgs boson mediation, dark photon mediation, or it could be a SUSY style mediation where you have, say, a neutralino, for example. Sorry, don't know why it's doing this. You can have apologies. Two neutralinos exchanging by, for example, by leptons, lepton annihilating to E plus, E minus. So there's each of these models have received enormous attention. So, all right. So what I'd like to point out, and that's been an idea in the last 10 years, that the mass range for dark matter can be very large. And this kind of seems surprising, because the first sort of idea of dark matter due to this annihilation was suggested by Steven Weinberg and Ben Lee a long time ago, and it sort of gives a range for the dark matter mass. They took exactly the kind of the weak interaction strength mass and sort of mediation, something of that nature. And their prediction was actually, if I remember, 6 GeV. So this, since then, that model has been long rolled out. But I'd say discovery, or sort of a thought of the last decade, is that the range can go much broader to MeV, for example, or even smaller. And that is achieved if, on top of the particles that are residing at the electroweak scale, such as here Z boson, Higgs boson, or lepton, you may have light mediators whose masses are relatively light, say a GeV scale, and therefore the whole scale of the cross section is not rigidly linked to the weak scale cross section. And that brings us to the ideas of dark sectors. This is so this is the neutral sectors that comprise dark matter, or may comprise dark matter, and interacting with the standard model in certain ways. If we're staying at really low energies, not LHC energies, but lower, the effective field theory is a good guiding principle, right? So effective field theory tells us that the Lagrangian of the standard model plus beyond standard model physics can be described by the standard model itself. A set of high-dimensional operators composed from the standard model physics, and so here I put starting from dimension 6, but famously dimension 5 can give you effectively the neutrino masses. Then there could be new dark sector interactions where the new fermions, gauge bosons, Higgs bosons of dark sector interacts between themselves, and there are operators that couple them, and these are lowest dimensional, sometimes called portals. The interactions build of these fields times the portal couplings. So this is if you say there is no new light degrees of freedom, you would just say, oh, that this first two lines is all what I have at low energy, right? And that was a dominating paradigm, but now we understand that it's way too restrictive, and we need to include this line, these two lines as well. So perhaps thankfully the number of these possibilities is limited inside the standard models. So you can have the so-called Higgs portal, where you take a Higgs standard model Higgs bilinear, and you couple it to a square or a linear term of the dark matter field, dark sector fields. You can take, and these are portals, and I would insist that this is lowest dimension portal, where dimension stands for canonical dimension and dimension of a photon or a Higgs field is 1, and dimension of the fermionic field is 3/2. Okay, and this is energy dimensions, and I'm using h bar equals c equals 1. Very well. So this is the Higgs singlet interaction. You can actually think of the Higgs as a heavy particle itself and integrate it out. In which case, this new particle S will or S squared will couple to the current created by the Higgs, and it will be a high dimensional operator from the point of view of low energy. Then there will be a kinetic mixing operator. That's important. You have one U1 factor of the gauge group, standard model gauge group. So that corresponds to the gauge invariant field strength B mu. That's a linear combination of the photon field strength and the Z boson field strength, by the way, right? And it has open indices, so you can check that you can sort of couple it to another gauge group, let's say from the dark sector, and that gives you a legitimate dimension 4 operator, as noted by Bob Holden long time ago. And that is as far as the bosons go at dimension 3 and 4. And then one can add another fermion and couple it to the lepton times Higgs by doublet, a composite doublet of the stellar model, and that is sometimes called heavy neutral lepton portal, because it's very tempting to assign a lepton number to n and declare it right-handed neutrino. So this is the most motivated portal because it is probably, possibly responsible for the dark matter, for the neutrino mass generation. And then stepping beyond that dimension 4 operators, well, there are some other groups as well, like gauged B minus L, L mu minus L tau, the standard model gauge numbers. That if you gauge those, they are normally free and can be sort of UV completed with or the B minus L is anomaly free, L mu minus L tau is anomaly free, but you need to work a little bit on the mass sector to make it a consistent model. Anyways, other than this, possibilities that do not actually require any new physics at the very high scales, there can be also dimension 5 and higher operators that do require new physics at some high scale, and in particular, important among them, the axionic portal, of which you will hear more during these lectures. So this is all as far as this the portal couplings go. Okay, very well. Now maybe I'll spend a few slides on how the fermion masses are generated in the stellar model and why the couplings between the left-handed and right-handed fermion supplied by the Higgs generates the mass for stellar model fermions, and how this is used for the neutrino mass. So the field content of if you Google the field content of the stellar model is given here. All the field content is fixed. If you say fix the charge of one particle, then all the rest falls out from experiment, if you like, except this charge that is defined for the Higgs boson plus or minus 1 modulo sign, right? Because this is not. That sign is ambiguous inside the stellar model. Anyways, the important part, one of the most important parts about the stellar model is that left and right fermions have different charges. That means that you cannot just take electron multiplied by electron left multiplied by electron right bar multiplied by fixed mass and put it in a Lagrangian that will contradict gauge principle of the Stern model. So what you are resorting to do is to put something like a new scalar and make this scalar wave. This is you know, a very interesting mechanism that gives masses not only to the leptons but also to the gauge bosons, and that was quite surprising when people realized this at mid to late 60s. So the mechanism for generating the masses for gauge bosons is not as transparent as it is for an electron, but it's reminiscent of a particle going through medium and experiencing sort of a forward scattering that shifts the pole over here by a finite amount. This is the photon going through a medium and receiving so-called plasma mass. This medium which photon is going through is unable to provide masses for W's and Z's in any seriousness because it breaks Lorentz invariance, because we're employing some thermal bath of some particles. However, if you make this particle scalar and you demand that the scalar has an absolute expectation value, then you can organize the very same way and shift the pole without picking up a preferred frame. This is a 5-sentence a summary for you of the famous papers by Higgs, Engler, and Brout. And so this way you get one member of the the complex phase of this Higgs of this field phi, even by mu giving its masses to gauge bosons. Very well. So many of you have heard about it. If not, here's you can ask me questions. So there are 4 scalars inside the Stern model and 3 gauge bosons. 3 are eaten by W plus, W minus, and the Z, and the 4th one becomes this very famous 125 GV Higgs resonance. Very well. So what about the neutrinos? So if you look at this field content that I lifted from the internet, but so you don't see the counterparts to the right-handed charged leptons. So therefore, you cannot just write this down this way, right? So instead, what you can do is to write a composite fermion where you couple a left-handed field to phi. This phi is a Higgs. This is the total singlet with respect to Stern model. All right. So it has a dimension 5½ as we just learned in the fermions, and the bosons have dimension 1 3/2. So to get the mass for the neutrino, you can just take this object and multiply it and put the 2 together like that. And the only care you need to provide when you do that, you need to contract the Lorentz indices in such a way that this becomes a total Lorentz scalar, and you can do it. And so this is an operator, the example, dimension 5 operator. So in my starting point over here, that would be included among these operators, for example. That this is a starting point for the neutrino mass once the Higgs goes to condensate. So you can see that the neutrino mass, looking at it as an effective operator, corresponds to dimension 5. So implies a new physics. So there is a very natural completion of this in terms of the exchange of the what's called right-handed neutrino. Right-handed is in quotation marks here, really. But it's a possibility if this right-handed neutrino has an additional mass, which is the simplest choice if this is a Majorana mass. That is a new, more minimal type of mass that you can have for fully neutral fermions. So this is the mechanism. The question is what this mass can be. It can be anywhere. It can be very large. Well, first of all, this model gives you a mixing, gives you one particle whose mass is roughly the mass of this heavy neutrino. Another particle mass is comparable to the Yukawa coupling squared, Higgs wave squared divided by mn, and there is a mixing angle given here, right? Very well, meaning that that would be sort of naively neutral particle can participate in weak interactions with the mixing angle that small, controlled by the square root of observed masses, ratio of observed neutrino masses to the right-handed neutrino mass. So this the interesting part of it, where is the mass scale of right-handed neutrinos? Well, if the Yukawa couplings are order 1, this comes in at around the God scale, and this is very interesting. However, the Yukawa couplings cannot be do not have to be order 1, and they can be much smaller as they are, for example, for electron. And in that case, the scale can be very low, and indeed all the way to 100 MeV kind of scale. And one of the favorite things that theorists play with the right-handed neutrinos is a leptogenesis, and that is the generation of baryon asymmetry, exploiting the lepton number violation, and that is can be done with very heavy neutrinos and also with GeV scale neutrinos. So this is there are some priors for this right-handed neutrinos, but it require the more sort of require additional theoretical assumptions, and therefore they're not solid. So the right-handed neutrinos can be anywhere. And they're well motivated, but then there is no reason to ignore all other portals here, and we'd like to study them. Here is an example of the simplified model for dark sectors built out of the dark photon portal. So what you see here is the interaction between the dark photons and normal photons. So this B mu times F mu factor, but F mu prime factor, but we've collapsed everything to low energy, so it's only the mixing with the photon that's important. There is a mass, possible mass to the dark photon, and there is an interaction of electron current with the dark current. Dark current could be a current of dark matter, and this epsilon parameter is likely to be small, and it's also interesting that it can be generated radiatively, and as being dimensionless parameter, it doesn't have to be small power-like. It does not have to contain a ratio, for example, of the weak scale to the new physics scale. and it can be generated at arbitrary high energies. So this is another example of the dark sector model. So based on these dark sector models, you can build everything, including the light dark matter, which you will hear more in the next lecture. So here's the two examples of the fully consistent models based on light dark dark matter and dark mediators. So here's the scalar dark matter interacting with the dark photon that has a kinetic mixing with this star model gauge fields. That is, and if you require this, you have annihilation happening in the P wave, which allows you to escape very strong cosmological constraints on energy injection during the late stages early stages of the universe compared to us, but late stages of the universe compared to the thermal freeze-out. And that is one model. Another model is equally simple. You take a fermion, you couple to a mediator, you ask the dark matter to be larger than the mass of the mediator. In this case, the annihilation goes chi to 2s to on shell to standard model particles that S decays due to the kinetic portal, mass portal with the Higgs. So this is this models occupy one line or half a line, and they can be very much dark matter candidates, modulated dark matter candidates, and they can be they need to be searched at all energies. So very well. So once people have that possibility sank in, I don't know why my slides are getting cut off, but anyways, once this possibility sank in, there was a new kind of interest in studying them experimentally, all these possibilities. And there is a large effort both in Europe and North America where you try to catalog all these cases and contrast them with experimental possibilities, where you look not just for the dark matter, right, but you look for the particles that interact with the dark matter as mediators. And here is a representative effort where we formulate models based on dark photons, model based on dark scalars, dark Higgses, models based on right-handed neutrinos, and models based on axions or axion-like particles. All right, so here's, I'm moving to the question of how to explore dark sectors in experiments, right? If you have Higgs, if you have very heavy, weakly interacting massive particles, let's say comparable to the weak scale, your only chance in the lab is to do what you do. Like if the dark matter is so weakly interacting that it penetrates in the underground lab, you may have a chance of detecting it through minute energy depositions it makes in the detector in the process of scattering. However, if you have it within a kinematic reach of your colliders, you may hope on seeing an abnormal energy loss associated with the pair productions of such particles. Moreover, if you have dark sectors that are, like I said, can be light, you have additional signatures where you can actually try to see more than just the missing energy. For example, you can put electrons and protons on target, and this is a common way of generating neutrinos, but you can also generate, for example, through production of light mediators with a subsequent decay to dark matter, you can generate not very focused, but still a beam of dark matter particles that passes through a large detector and does something, right? So, or rather, this, like, let's say this is your initial starting point. Then you can produce the dark sector particles that I can have sort of finite C tau. They can propagate, and then they can decay in the detector. That would be abnormal energy release. You can produce stable particles such as light dark matter that can fly into the detector and kick one of the nucleons or an electron, and that will or do something else, and that would constitute again a signature. Then the dark sector particles may manifest themselves as a force. So, for example, if the neutrino enters the detector, it could have an interaction on top of the standard model interactions. And this is very powerful way of looking for new physics, because neutrinos have very little interaction. So if you see that interaction, you by default already very sensitive. So that's another way of looking for new physics. You can have neutrino oscillating into a new state and disappearing. That would be a member of dark sector in this sort of more comprising framework I'm talking about, and many possibilities. And with particle beams and particle colliders, you of course have a golden possibility of studying missing energy and momentum in collisions where particles are sent on target one by one. Or one can detect abnormal energy losses, such as, and also, you know, in particle colliders, you will look for something like a single photon plus a large amount of ascribed energy loss, and if this is above the backgrounds predicted by the star model, then you have to really work further to understand whether this constitutes a real signal. Very well. So going back to this list of models, all these models are being confronted with various experimental proposals, either existing or in progress, or just ideas. Among this, there are indeed existing experiments and A62 funded experiments such as Phaser and then being built, and some really, I'd say, this is an existing experiment, and some daring, and this is like an animal world here. There is like a great variety of experiments, from very small, such as millican, to ginormous, such as Methuselah and Ship, where these are very expensive experiments, and it's a question whether they're going to be pursued. Very well. So anyways, doing this and going through existing data and analysis from the all the other experiments that bothered to look at this, we can sort of start compiling exclusion plots. That is to say, we haven't found anything. And there is a large exclusion areas based on the parameter space of models I gave you, where I start with the dark photon business. So in the dark photon, it's important to mention that actually over here there will be a range of couplings and masses where muon G minus 2 can be corrected in the right way, but unfortunately, fortunately, the experiments have ruled out that possibility for a minimal dark photon a long time ago. When I say minimal dark photon, I assume that dark matter may be heavy, and what you have is the dark photon at low energy, in which case you just look for its creation and decaying at the distance. So if you look at this plot, you will see two groups of probes. That this is roughly one group, and this is another. So if this I call the first group, here the decays are prompt, and what you're trying to do is to look for abnormal peak at any given mass of the electron-positron pairs. That's why there is this jagged sort of ends to these exclusion regions, because these experiments are incredibly resolving in terms of that parameter. Another group of constraints comes from the beam dump, then passing through dirt and decay at a distance, right? At a distance where dirt has a wonderful, it's a slang, but it has a sort of filtering effect, and then if you have abnormal energy deposition, you can exclude more. So this is how it looks like for the dark photon. If the dark photon decays invisibly, however, your number of options shrinks quite a bit. So what you then looking for is the missing energy, and you can do it with B factories. K-on K to pi nu. This is sort of if you have a production of two light dark matter particles, it would be just a correction to this, and since it's consistent, that's how it would look like, and then consistent with the Stern model. And then you can also have a dedicated search of missing energy and missing momentum, where the world's leader is Na64 experiment. Very well. You can also have, you can say more. Let's say dark photon does decay to light dark matter. And in this case, mass of dark matter is 1/3 of the mass of the mediator. And then you can predict where this mass versus coupling would sit on the parameter space. So this black curve is really your target at that point. And then you can have various other experiments, such as neutrino experiments. You can't see here, but it's written LSND. Which is an experiment that has put largest number of particles, protons on target anyways, all macroscopic amount, and almost 1 gram of protons on target. And then there is the other experiments where you try to produce the dark matter and see it scatter, right? But then at the same time, there are more constraints coming from experiments where such as Na64, that's been extremely successful, where you look for the missing energy. And I should just a general comment here: the experiments that look for missing energy have advantage over experiments looking at production and detection because they scale as epsilon squared versus epsilon to the 4. However, in case of positive signal, it's harder to decide what it could be. All right. So, and here is how the mini-boon search for light dark matter looks like. So, for example, in a dedicated run, the otherwise neutrino experiment would steer the protons around the beryllium target, so there is as little neutrinos produced as possible. Dump it into the beam dump, and in this model, based on dark photons, the leading mechanism of its production would be pi 0 and etas decaying to photon and dark photon. Then later, the dark photon immediately decays to two dark matter particles that fly in and scatter on, say, nucleon inside the detector. And so this way you can really set new constraints on the parameter space of this model. And this is I won't spend much time on it. So constraints on dark scalars are being analyzed very well. So this is in units of the mixing angle between the Higgs and the scalar that is given by this operator. When it goes into Higgs goes to condensate, you get A times V scalar times the Higgs. So this is basically the mixing angle is the ratio of this parameter to a mass of the Higgs squared. So in terms of this parameter theta, everything is analyzed, and you can see that there are constraints from cosmology, astrophysics, and there is a lot of constraints coming from the flavor experiments, and that is because there is a reason that light scalars are more happily produced in the decays of the kaons and the B mesons, because they correspond to the scalar current that is having different properties under radiative corrections than the conserved U1 current based on for example, compared to dark photon, for example. Anyways, and these new projections are aiming to explore much more of the parameter space in this model. The constraints on heavy neutral leptons are I don't know what happened. Sorry about that. Are comprised over here. So there are constraints. So to produce heavy neutral leptons, if they are in the kinematic reach, you need well, basically charged weak currents, and this is therefore more sufficiently produced at the proton collisions, because protons produce a lot of mesons whose final stage of decays, such as pions, for example, or kaons, often, or in case of charged pions, necessarily result in the production of neutrinos. So you produce this that way, and then they typically have a long decay lifetime, and you try to detect abnormal energy deposition. This is done, you see here in the old experiment called CHARM, as well as well, other experiments, including also the very sensitive probes from W and Z decays. and the pair productions of the and the single productions of these new particles. So this is done for electron. Neutrinos, as you know very well, contain additional flavor structure, and here there's very sort of crude simplifying assumptions that they're coupled either to one flavor at a time, to electrons, muons, and there is a corresponding plot for taus that I don't show. All right, and the final maybe have a minute or two, then you can also probe for some additional particles in neutrino scattering, Z prime. So here is, for example, how the scattering on the neutrino of a neutrino, the normal neutrino scattering looks like this, right? You have a neutrino coming in. Sorry, it's an electron. Okay, fine. Here is the neutrino. Here's a W, here's a neutrino, here's an electron. That's for example, a scattering of a neutrino and an electron studied in very many sensitive experiments. And if on top of this you have some sort of Z prime, let's say mediation, some additional force, you can set additional constraints on that. It is clear that this additional force mediates the Yukawa interactions between the particles, and then the strength of that interaction in momentum space, the amplitude for scattering, has a g squared divided by characteristic q squared plus the mass of the mediator squared. And that is square of that, which is what you miss determining an experiment. Moreover, each experiment has a very characteristic q square that it studies, and that explains this type of shape with the kink, where this corresponds to a typical q square in the experiment, right? And that is at a small mass mediator, you don't have any sensitivity to the small mediator mass, and that's you can see that very, very weakly coupled forces can be probed using the neutrino experiment. And then one could even do more fancy things and revive an old searches for dimuon production for neutrinos. Is a well-hidden process inside the Stern model that allows you to look at new models of dark forces that includes all mu minus all tau. As I mentioned, there's an anomaly-free combination of the Stern model. So that why this is this beast is interesting, because neither muons, no taus, or their neutrino counterparts provide any target for you to shoot at. However, if you have a nucleon here, for example, then you can create the pairs of the muons by merging a virtual gamma from a nucleus with a Z prime this way and producing a pair of muons that this turns out to be interfering constructively with the Stern model. And so if this new encircled thing here provides as much amplitude as the Stern model, you should see 4 times more events, and you don't see it, and then you set a very kind of interesting limit that is further improved by the search of fermions at Babar and the search of fermions. This being improved somewhat. I don't have the latest plots by the CMS Z to fermions case. Very well, but the interesting part is that muon G minus 2 can still be solved by L nu minus L tau if the mass of this gauge boson is below 2 mu, in which case it decays to neutrinos, and if you produce it alive, it just doesn't register as muons, and this type of mechanisms, which I should say called the trident, are not as effective because if the Z prime is very light, you get a form factor, and you don't produce it with the same energy growth as the for heavy Z prime. And that just tells you that there is a large part of the Prandtl space that is still available for a possible solution of the G-2 discrepancy. Okay, that way. All right. So, oops.